Let us quickly prove this and then we will use this. Okay, what is the proof for this? The proof is that you have some amount of liquid entering here. But let us think about this whole liquid that is inside and think in terms of the change in energy of this liquid. Suppose I didn't know that pressure was like spring energy. What forms of energy will I talk about? Kinetic energy and potential energy. But then there is a force here and there is also a force there, and that force is related to the pressure here and the pressure there, because the liquid just on that side will be pushing and the liquid just on that side will also be pushing, right? So therefore we should be talking about the work done by these forces, and that should change the energy of this liquid, right? But like we did earlier, if I start by saying, okay, this portion I am just happily going to ignore. Now what is so special about that portion? This length, let us say, is V1 and this length is V2. So what can you say? What do you know about this portion? We have done this enough times with continuity questions now, right? So what can you say? Correct. You know A1 V1 is equal to A2 V2. That of course you know from continuity. But you also know that this liquid that I have drawn there will come to this place. And this liquid will get out of that place. Right? But whatever comes in here will continue to have the same velocity that it had earlier. So if I want to talk about this entire thing's kinetic energy, I can do this in an interesting way. What I am going to do is, now I can select the system the way I want. I am going to select my system from here till there. My system. Work done on my system must be equal to change in kinetic energy of the system. But the kinetic energy of the system has two parts. X, Y, right? Initial kinetic energy, not kinetic energy, initial kinetic plus potential energy is X portions initial kinetic plus potential plus Y portions initial potential plus kinetic, right? Then if I want the final kinetic energy plus potential energy, what is that? Well, when this guy comes in, this fellow goes out. So where is my new system finally? Not new system, old system, but after some time new position. What is it? So this is the final, this is the initial, right? It starts here until there, that is my same system. At the end. But the system now has a Y and has a Z. So what is the final energy? Y plus Z. There is no X. So if I try final minus initial total energy. Well, it's technically not total energy, but kinetic plus potential energy. Delta of kinetic plus potential energy is how much? Z minus X. Hopefully I can calculate this. We will calculate it now. Okay. But the change in this energy must be equal to the work done by other forces. Who are the other forces? Well, this force and that force. What about gravitational force? I have already counted it as potential energy. I can't count it again. So I am not going to worry about work done by gravitational forces. But I do need to work done by this force. But the work done by this force is easy. What is the work done by this force? Let us calculate the work done by this force. Work done by this force plus work done by that force over this period of time. In that 1 second. In this 1 second, what is the force, by the way? A1 into P1. So P1 A1, but that's only the force, work done, into distance moved. displacement in the direction of force V1 plus work done by that force. But what is the force in this direction? P2 here, P2 into A2, but it's moving in that direction. What is the work done? Minus P2 A2 V2, because it moved V2. Of course, we know that A1 V1 is equal to A2 V2. So what is this? If A1 V1 is equal to A2 V2, I can write it as P1 minus P2 into A1 V1, or I can write it as A2 V2, whichever way I want. Right now, I'll just write it as A1 V1. You know that because this A2 V2 is the same as A1 V1. I'm not going to replace V2 as A1 V1 by A2. You know that you can just write it as A1 V1 or A2 V2. Okay. So this is the work done. Work done is the pressure difference into the volume of the liquid that comes in to the old place or gets out of the old place, whichever way you think. Right. Now let's calculate this quantity. What is Z? Z is the amount of energy there. How much is the amount of energy there? Well, potential energy plus kinetic energy. Correct? What is the mass of the material there? A2 V2 rho. Mass into G into H. So G into H. H2. That's straightforward. Plus mass into V square by 2. Same mass, no? So I'm not going to write V square by 2 again. I'll just write V2 square by 2. Mass into GH, mass into V square by 2. That is the energy at Z. What is the energy at X? Mass into A1 V1, which happens to be anyway equal to A2 V2. Right? And then potential energy there, GH1 plus V1 square by 2. This is Z, that is X, so the difference is this minus that. The great thing is that these two fellows are common. Why? A1 V1 is equal to A2 V2. What is it? It's the volume, but right now we'll just ignore it. We'll call everything as A1 V1. I'll only call A1 V1, A2 V2. I will not change these fellows. I like it as it is. But this difference is equal to that. Correct? Because the work done is equal to the change in the total energy. So if I equate this minus this to P1 minus P2 into A1 V1, remember A1 V1 is equal to A2 V2 is equal to A1 V1. So if I look at this and combine, so this fellow has rho GH2, rho V2 square by 2, and then there is a P2. So if I bring that P2 here, you will end up with everything as P2 plus rho GH2 plus rho V2 square by 2. And if I take this to that side, I have P1 plus rho GH1 plus rho V1 square by 2. But that is Bernoulli's statement, right? So we have proved Bernoulli's statement. So what is actually Bernoulli's statement saying? Work done by the pressure here plus the work done by the pressure there, that is negative, this is positive, but the work done overall has changed the kinetic energy plus potential energy. And when he rewrites the statement, it looks like this. So now you can think of the idea, instead of talking about it as work done, you can say pressure energy plus kinetic energy plus potential energy is a constant. So what is this pressure energy? Well, that is the pressure into volume. But what is pressure energy? Because the molecules are closer, the more the pressure, more spring effect. So effectively more compressed springs. So therefore more energy stored at the molecular level. And if they have spread out a little bit like that, less energy at the molecular level. But the molecular level energy plus the energy that you have for bulk matter moving, which is the kinetic energy, plus the height increase, which is the potential energy, the sum of the three energies must be constant. When Bernoulli came up with it, of course, he didn't know that this came out of intermolecular forces, but it's a great equation. He just used work energy. It's still work energy conservation theorem. So is everybody clear about this? Okay.